Okay. Bisa. Bisa ba tulis? Oh, belum di-on ini nggak, Bang? Itu. Kalau nggak,
Jadi sebenarnya nggak bukan gitu ya. Okay, finally lecture ready. Okay, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, and our apologies for the technical problem that has taken some time. So we were scheduled to start at 1, so it's almost 1 hour delay now. So, well, I will try to make the remaining time enough for us to discuss what I plan to deliver to you today. So this is the title, yeah, I changed last time, right? I modified a little bit the content. I reshuffled a little bit the order. So basically, the thing I put as number 50 was somewhere up here, which now I'm not sure whether I will have time to cover this one. If not, then probably we'll just cover the line itself. Okay. All right. Yeah, let me jump to how to go there to see this okay, this is our last part, right? Now, so we are coming to this part. So we are going to start to do math. So for the rest of our discussion today, we are going to do the analysis using classical mechanics, electromagnetic theory, and also at the end, we also incorporate quantum mechanics. Okay, so to describe the transport and optical properties of metals and insulators, the easiest way we can start with is by applying classical mechanics. That's what was done by Drude, and then later on it was modified also by Lorentz. So the whole model has been known as Drude-Lorentz theory. So the Drude part was basically about the metal part, where the Lorentz part is for the. So consider a metal under irradiation of the electromagnetic wave, something like this. So I made a cartoon where you can see, let's say, circles representing atoms, and the red the red color is representing some electron clouds forming like waves, something like that, right? So that some concentration of electrons right here, some region where electron is less, okay, some oscillatory motion of electrons. So this, imagine that this metal is under irradiation of electromagnetic wave like that, and the electric field carried by the electromagnetic wave has the time dependence that goes like this. Okay, you don't need to worry about partial dependence, because what we are what we are focusing is the local area in the material. Okay, so this is our assumption that lambda of the electromagnetic wave is so large compared to this parameters, the distance, average distance between adjacent atoms. So because of this, then logically we can expect that the position of the electrons will dynamically change following the time dependence carried by the electric field, right? So this is simple logic. Okay. So by R, it means the relative positions of the electrons with respect to their equilibrium positions. So wherever the electrons have their equilibrium positions, they are the 0 points of the electrons, and R represents the displacement from those certain points. Okay. So we simply apply what equation is this? What law is this? Newton, right? Yeah. So this is m times a, right? And on the right hand side we have the. So we have two forces here. The second one is the one that is exerted by the electric field carried by the electromagnetic wave. And we need to add another term, just first one in this case, which should be there because otherwise, if the electrons are only affected by the electric field, then the electric field will tend to, if it is constant, it will tend to accelerate the electrons forever, right? So there wouldn't be any equilibrium steady state situation. So in order for us to have the steady state situation, we believe that there is a mechanism inside the material that can restore back the equilibrium of the electrons after receiving the influence from the electric field. The mechanism is usually collision between the electrons, and basically anything that acts as obstacles of the motion of the electrons. Okay, so whenever electrons see anything that can disturb their motions, they become the obstacles of the electrons, and with those sources of obstacles, electrons feel the collisions. And we put a parameter that I call tau here to represent the relaxation time. The relaxation time means the time where electron is being free for a while, okay, before it encounters another collision. Okay, so make sure that you know how to guarantee that this equation is correct in terms of the dimensionality, okay, and also the sign. Of course, this sign has to be minus because the effect should be decelerating. The effect of collision should be decelerating. And this also has minus sign because the sign of the electron charge is negative, right? So simply we substitute these two time dependence into this equation, and that results in this relation without having t dependence anymore. But now we have the omega appearing in our equation. Okay. Then from there we can conclude that the R. So we are basically seeing just one electron. Okay. So every electron is experiencing displacement due to the electric field that gives us this relation. Okay. Then, if you remember that every time we have a situation where there is a separation between positive and negative charge, then we are creating what we call dipole, right? Electric dipole. So electric dipoles are vectors, okay? So if we sum over all vectors of electric dipoles, we get what we call polarization. P is defined as polarization. So this polarization is sum over vectorial sum over all electric dipole moments, or we can say also not only dipole. That's all right. Theoretically, we have to put 1 over volume in there. Okay. So if you want to put a note about the definition of polarization, it is vectorial sum of electric dipole moment, all the electrons divided by volume. Okay. And since we are simply looking at the average, then the summation over all electrons can simply be placed by the density. So N is the electronic density, the number of electrons over volume. Okay. So R is kind of average of all electrons. So this is what we get. The polarization related to the electric field. So here's the issue. Once we know how the electric field induces polarization in the material, then we have the displacement vector. You remember from the electromagnetic theory, right? So we define the displacement vector in relation to the electric field being, so the D is equal to E times epsilon, which is in this case not the epsilon 0, but not the epsilon naught, right? The epsilon of the vacuum, but this is epsilon of the material, of the corresponding material. So if we relate it to the epsilon of vacuum, then we have to put proportionality factor, which is so epsilon R stands for relative. So epsilon R is relative permittivity, which is the permittivity of the medium divided by the permittivity of vacuum. Okay, and we should be familiar with this relation that B is equal to epsilon naught E plus P, right? So applying the P that we obtained in the previous page, so we can rearrange our equation that leads to this page. Okay. Next, since this is a complex number, see there is an imaginary number over here, right? So the whole number is complex. So every complex number can always be decomposed into its real and imaginary parts. If we do so, then this is what we need. Okay, real is what it is. Okay. So these two quantities are important and each has its own physical meaning. If we focus on the real part first, when the real part has the value of 0, then the omega value that corresponds to the root or the 0 of G epsilon 1 is called plasma frequency. Why is this called plasma frequency? Well, let's think about that. We come to that. And simply if we do math, taking this to be 0, then we can extract the omega, and this is the omega that we get. This is what we call plasma frequency. So for the moment, let's understand that what we call plasma frequency is the frequency that leads the epsilon 1 value to be 0. Okay, but later on we will see the physical meaning of that. There should be animation, which I don't know why. Okay, forget about the animation. Well, that derivation was was a bit simplistic because we only focus on the free electrons. If you want to improve a little bit the model, then we may consider also 4 electrons. And in doing so, it amounts to replacing number 1 in that formula with some other value. Is 4. Sorry for the interruption. Okay, just improve the model with some rough correction by adding the role of 4 electrons or electrons they are not so free, right? Let's say that's the correction that we want to add. The correction will go to what we had one initially. Now we replace it with epsilon 1 infinity. Why we put this symbol? It is simply because when we take omega going to infinity, this is the result select. Okay, so that is the reason why we name it epsilon 1 infinity. So this is just a correction. So finally, after the correction, this is the formula of the plasma frequency that we have. Okay. At this point, I also would like to introduce to you another quantity that is called loss function, that is defined as the minus imaginary part of 1 over the complex permittivity. So if we work it out, this is what we get. This is the formula. What does this mean? Loss function, as you will see how it behaves. Okay, this has the physical meaning of indicating when the electrons absorb energy the most from the electromagnetic wave to form collective motion that we call plasma oscillation, or since every oscillation can always be viewed quantum mechanically into something that behave like particles, then later on we will call the plasma oscillation to be plasma. So this loss function is basically quantifying whether or not our system has plasma. Okay. Okay, this is the sketch of all the quantities I have described before. First, look at this curve with long dashed line, right? This is epsilon 1. So as you remember, epsilon 1 is some value epsilon 1 infinity minus blah blah blah, right? So if we take omega equal to 0, that will lead us to get the epsilon 1 value to be very, very negative. So if tau, let me go back to this page. If this tau is considered very, very large, for good metals, tau is very large because by tau being very large means that the electrons only very rarely collide. Okay. If tau is so short, that means the electrons very frequently collide. So if tau is very, very large, then at omega equal to 0, the value of epsilon 1 at 0 is really -3. Okay, but that's not the realistic one. So it's actually very, very, very high value of negative sign, but it's not finite. Okay. And so it behaves such that from down below it increases and it passes through the horizontal axis, and it will go asymptotically to the value that I call epsilon 1 infinity. Okay, which can be approximated to 1 if we simply use for the result. Okay, and this is the epsilon 2 according to the formula. This is the curve. Okay, and for the loss function, it turns out that the loss function gives us the behavior that it has the peak standing exactly coincident with the position where we have the crossing the 0 for the epsilon 1. Okay, so conventionally, these two quantities, epsilon 1 and the loss function, both characterize the presence of plasmons. So whenever we see that our quantities, the two quantities behave like this, so we say that we have plasmon, especially what we call bonds. But in a modern picture, it turns out that for the epsilon 1 curve, for indicating the presence of plasmon, it is not something necessary. I mean, we could have plasmons even without having this situation, without having 0 value for the epsilon 1, provided that we still have the peak in the loss function curve. Okay, so now we believe that the best quantification to describe the presence of plasmon is this curve, loss function. So whenever we have peaks of the loss function spectra, that is in those corresponding to all those peaks, we have plus. Okay, so whether or not plasmons are important for us, that's something we are not going to focus in our discussion yet. Okay, except if we have some time at the end of our discussion, which I'm not sure. Anyway, so this is the physics that is at the moment most important for us to understand first. The consequence of having negative values of the epsilon 1. Okay, if we go back to the curve, this region, see, so this region corresponds to epsilon 1 being negative, right? So as omega is above 0, but below omega p, epsilon 1 is negative. Okay, what's the consequence of epsilon 1 being negative? In this region, epsilon 2 may have some finite value. It may also have the value very, very close to 0 in this region. It doesn't matter much whether it has some positive finite value or it is close to 0. If epsilon 1 is actually negative, because the effect of epsilon 1 being negative, we will see that it corresponds to making the electromagnetic waves entering the material become decaying. Okay? Decaying. If it is decaying, that means it doesn't propagate. Okay? It doesn't go to the material. If it doesn't go to the material, that means, of course, the energy cannot stop without flowing anywhere. It must come back. Come back to the medium where it comes from, right? So that means it causes reflection. Okay? So that is actually the explanation of why metals are good reflectors, especially for the wave of this frequency. That's precisely the region of frequency of the visible light. So if we talk about electromagnetic waves beyond visible light, which is in this region, then metal is not reflective. Metal may be something that the wave can simply approach. Okay. So to be more quantitative, okay, as epsilon 2, let's on the region where k close to 0. Then epsilon r becomes negative, becomes a negative real number, but we are interested in looking at the square root of epsilon r. Why the square root of epsilon r? Because we want to connect it to k, the wave vector. Okay. Recalling the definition of what is this? Index of refraction, right? Index of refraction is ratio of speed of light in vacuum to speed of light in medium. So we can use the definition of omega over k. So omega over k naught divided by omega over k, leading to k over k naught. Meanwhile, we can also take the definition of 1 over square root epsilon naught mu naught, right? Like this. As we proceed the math, then we'll get that n is equal to square root of epsilon r mu r. Keep in mind that in this case, it is customary that we limit our discussion to non-magnetic materials. Usually, the theory of optics, most of the time, described in most books describing optical properties, they assume that what they talk about is non-magnetic materials. Because if you deal with magnetic materials, there are more complications. Okay, so for the moment, we limit to what many people also actually. So by non-magnetic material, it means that the value of mu r is simply 1. So mu of the medium is just the same as mu of vacuum. Okay, so mu r is 1. So taking mu r equals to 1, then n becomes simply equals to square root of epsilon. Okay, since this is equal to that, so we conclude that k equals k naught square root epsilon r. As before, we have concluded that in our case, when omega is less than omega p, this square root of epsilon r is square root of negative number, which is imaginary, right? Square root of imaginary number is in square root of negative number is imaginary. So that means K becomes purely imaginary. K becomes purely imaginary provided that epsilon 2 is assumed to be 0. If epsilon 2 is not 0, then K may be not purely imaginary, but it must have some imaginary part. Okay, significant value of imaginary part. So basically, it doesn't matter whether we have the real part or not, as long as we have the strong imaginary part of the K, then we will have strong decay of the electromagnetic field. Okay? So this implies that if we have this solution of electromagnetic wave, then we replace the K with I kappa. Substitute K with I kappa. Then we will suppress the I that gets multiplied with R, leaving only I and that gets multiplied with T. So we still have the oscillatory behavior for the time dependence, but not for the R dependence. So the R dependence simply immediately decrease. Okay. So this is the quantitative explanation of why metals reflect light, especially the light of the frequency that is less than omega. Okay. And as you have seen, omega p, the value of omega p depends on several factors. Predominantly the electron concentration, also the mass of the electrons, and also the collision time. So there are several factors that determine the value of omega p. So that omega p value will put the limit for the electromagnetic waves, whether we get the result of reflection or penetration. But typically, most metals have the value of electron concentration and other quantities such that the typical omega p value of most metals, natural metals, okay, fall into some value around EVs, a few electron volts. Why I'm saying omega, but I'm using the unit of electron volts? It is simply because, as we have understood quantum mechanics, whenever we talk about frequency, we can always easily connect it to energy by simply multiplying omega with what? H bar, right? So whenever we have omega, we multiply omega with H bar, we get the energy, right? Therefore, although I'm using the term frequency, for instance, but nevertheless, I'm using the unit electron volt, which is the unit of energy. So don't be confused, because energy and frequency, once we have understood quantum mechanics, they are just multiplied by constant. Okay, so this is the conclusion. The light doesn't propagate in. Okay, and it turns out that metals is the only material that truly reflect visible light. Okay, so what I mean by that is, if we see some other material that can reflect light, for instance, this kind of glass, definitely we are seeing reflection, right? We also see reflection from this glass, but we also can see through, objects that are on the other side, right? Meaning that there is, in addition to reflection, we also have transmission, right? Meaning that the amount of intensity that is reflected by glass is not that much if compared to what is done by metals. Metals almost 100%. Okay. So this is the process. If we have the electromagnetic wave coming in, strikes the surface of metal. So this is vacuum, this is metal. Then the electromagnetic wave immediately decays. If it decays, that means it doesn't propagate. If it doesn't propagate, that means it will eventually come back. Okay. This quantity, the depth of how deep the light can go in, can be defined as 1 over this kappa, and this is called skin depth. Skin depth is how deep actually the light can go into the metal, which is typically of the order of perhaps few hundreds of nanometers, which is very, very thin, right? That is why mirrors that you have in your home normally are not made of whole lot of metal, right? Because it's going to be heavy, right? You usually make the mirror by using your main material is actually glass. That's glass is like that, right? And you do coating. You coat the glass with just a few layers of metal. Why only thin is enough? Because this is thin. Okay? So you only need to have the thickness of the coating simply exceeding this value, which is just of order of few hundred nanometers. That's why if you have like a few microns of thickness of the metals that you call on top of the glass, that's very, very simple to serve as mirror. Okay. Okay. So let's talk about the quantitative explanation of why metals are good reflectors. Now I want to show you connection between charge transport and optical properties. So we have learned that charge transfer property can be quantified by conductivity. So that is actually the material covered by Dr. Adam, right? In this session about transfer properties. So he mainly talk about when we talk about charge transport, usually we talk about conductivity. Okay. Whereas when we talk about optics, usually we talk about permittivity, as we just did before, right? And these two are actually connected. Why are they connected? Because they come from the same physics concept, which is Maxwell electromagnetic wave. Okay. So these are Maxwell equations. Remember, the US have learned this, right? So there are 4 equations covered by Maxwell equation, and we are interested in a situation where the first one, the one that comes from Gauss law, we take the right hand side to be 0 because we want our system not to be charged. So the total charge of the system is essentially 0. So that's why it is 0. And divergence of B is always 0. And then curl of B, curl of B is from Faraday's law, it is minus rho B dot curl of E, sorry, rho B dot T. And then curl of B consists of 2 terms. This is the important part of this discussion. When we talk about materials that don't have conductivity, when there is no conductivity or if the conductivity is 0, then this term will be zero because we also need to apply Ohm's law. This is Ohm's law. Do you recognize it? Yes. Just remember that when we say Ohm's law, your thought may associate Ohm's law with the macroscopic Ohm's law, which is V equals to I R, right? That's the macroscopic version of Ohm's law. But this one is the microscopic version. Current density equals conductivity times U. So because of this quantity being non-zero, because of the presence of sigma in our system, then the last equation of the Maxwell equations can be written to explicitly show up the sigma dependence like this. Okay. Okay, now let's do the math. Let's take the curl of curl E. So take the curl of this one, right? So if we take the curl of curl E, that means we take the curl of B over here, right? And there's an identity. Curl of curl give you these two terms. This is part of mathematical method. Mathematical method of basic definition. You should also have that, right? So I'm not going to prove this. So as this has become mathematical identity that you should be familiar with. So the left hand side has two terms, but the first term is actually just zero because of the first Maxwell equation. So we are left with the second term. Okay. So finally, this is what we get. So this is actually the differential equation of the light in the material that has conductivity. So if we simply set sigma to be zero, this gives us the usual differential equation of light for traveling in vacuum or in any material that doesn't have nothing. Okay, so it's simple wave equation. Next. Now let's consider first sigma being zero. Then if sigma is zero, we know that this is the solution. Okay. By the way, I believe that you have studied math physics up to differential equation, right? Partial differential equation, complex variable effects. So that you are familiar with the solution of this kind of differential equation, right? Especially when we simply drop this term, the solution is easy, which is this. Okay. So if we take this solution into the differential equation, this is what we get, right? This is what we get, and then we can conclude that the wave vector is related to the frequency and the square root of epsilon naught mu naught like this. So this is actually 1 over speed of light, right? So this is the familiar expression. I intentionally didn't write it as omega over c because I have the purpose of exploring the epsilon in the next equation. Okay. Now, when sigma is not zero, then the solution may have the form that is just the same as the one before, only that we have to consider that. So the K is something different. Okay? And what is that? In order to know what is the new K, we simply write first that the K here is something different. Let's name it as K tilde. And then we simply substitute back this solution to the equation where there is a term that remains sigma, right? Now we don't have only two terms, but three, right? The left hand side has only one term, but the right hand side has two terms. So this is the connections, the relation, and then we can extract the K tilde, and I intentionally make the structure of the equation such that it has a similar structure with that one, right? So then you realize that I could actually write in a way that doesn't look like this. Okay, it can be up to me, right? But I intentionally made it in such a way that if I compare this expression with the one on the top, then I can have a comparison of this quantity epsilon naught with this quantity, which is epsilon naught plus something. Okay, then I can associate this new epsilon naught as to be my new epsilon. So now, rather than saying that my medium has permittivity equal to permittivity of vacuum, now I have the medium with permittivity described by this permittivity. Okay, this complex permittivity. It is no longer real and constant, but complex and actually frequency dependent. Okay, and what is that? As we can extract from here. So since this is complex number, so epsilon tilde become a complex number. And again, we are interested in exploring not the permittivity itself, but the relative permittivity. So we need to divide this by epsilon naught itself. So dividing this by epsilon naught, this is right. Okay, initially I didn't say that sigma is complex, right? Since I always say that I'm considering that my material has conductivity, but I didn't say that my conductivity is complex. So let's say that I was assuming that my conductivity is a real number, but when now I have come to this relation, if I'm considering that this is a complex number, and if I consider that sigma is just a real number, so this is real, this is the imaginary part, right? Meaning that the real part of epsilon r is just one, and the imaginary part is just sigma over epsilon naught omega, which is actually not consistent with what we have learned before, right? We have learned before that both epsilon 1 and epsilon 2, both the real parts and the imaginary part, actually have frequency dependence, right? So if I conclude from here that epsilon 1 is just a constant of unity, right? That's not correct, right? So what makes it not correct is what? What makes it incorrect was the assumption that sigma was real. So we have to change our assumption that sigma now has to be a complex number too. Okay? Now, considering that sigma is now a complex number, then we can rewrite the relation between epsilon r, which is a complex number, with sigma, which is also a complex number. I forgot to put sigma dependence over here, but it's not very important. Okay. So as now we want to break down both quantities epsilon r and sigma to be the real and imaginary parts, then I can write, right? So if I break up epsilon r into its real and imaginary part, can write it like this, and also write sigma to be sigma 1 plus I sigma 2 like this. Then I can extract the relation between the real part and imaginary part from the permittivity side and the conductivity side. So this is what we obtain. So I put the boxes, red boxes, beside they are on the page. Okay. See, now we have understood that talking about transport properties, with the discussion of optical properties. Therefore, whenever we are seeing something from the transport measurement, don't underestimate that it would actually just tell us about the transport properties. It actually can be an indication of something going on if we investigate the optical properties. So that's actually the lesson that we learn. Okay. Okay, thanks. What we derive from the truth theory were actually epsilon 1 and epsilon 2 only. Okay, only epsilon 1 and 2 that we explicitly derive using the truth model. Okay. We didn't do the division for the conductivity. Okay. So if we want to derive the frequency dependence of sigma 1 and sigma 2 directly from the model, we could do it. We can go back to starting with writing the Newton's equations with the substitution, but rather than defining the polarization, we want to talk about conductivity, we need to define our density. Now there is a way to do so. Okay? But we don't have to do so if we already have the relations between sigma and epsilon. So provided that we stick with the same model, if the model has given us epsilon, then we should be able to extract conductivity from the results of the model. Okay, so this is what we get if we simply use the epsilon 1 and epsilon 2 we obtain from the truth model. Okay, it looks simpler. Where in this case, sigma BC means sigma for, okay, here's another important point. Although the relation that I'm showing here is a frequency dependent relation, but we can still connect it to the DC phenomenon. You can imagine simply that whenever when you apply DC voltage, you can still use this theory, although as a matter of fact you only apply DC voltage. How do you use this theory for DC conductivity? It is simple. By DC conductivity, it means the conductivity associated with constant voltage, right? By constant voltage, it means constant electric field too. Okay? Constant electric field means it can be associated with the oscillatory behavior, time dependence, by setting omega equal to 0, right? Meaning that from the whole function that we have obtained, you simply take the omega equal to 0 result. That gives you the sigma. All right? And that the value is NE squared tau over M. So that should be something that you have learned from Dr. Adam, I believe, right? If not, then something is missing. Okay. All right. So here's the typical curve of sigma 1 and sigma 2. So this blue curve is showing you sigma 1. So sigma 1 is actually what measurement usually directly can measure. Sigma 1 is the what we call optical conductivity. Okay. So normally in experimentalists showing you optical conductivity curve, that means sigma 1. Okay. Sigma 2 is not something that they probably can extract directly from experiment, but by some indirect method, they can also obtain signals. Okay, so there is a certain characteristic that you should be familiar with. As you remember, this is showing you the optical conductivity profile of a metal obtained using the Drude model. Okay. As a characteristic of a metal, it has, this is what is called Drude peak. By Drude peak, well, Drude is a person who derive the theory, right? By Drude peak, it means this characteristic is only there if the system is metallic. If the system is not metallic, there won't be any such a peak. So this peak signifies that the system is metallic or a conductor. Okay. So if there is no Drude peak, that means the behavior is what? How would the curve behave if we don't have the peak? If we don't have the peak, that means we may have something like this, for instance. Right? So rather than the peak, we have the value over here. Okay? So if that is the case, then the system is not quite metal. If it is actual insulator, if it is real insulator, then the value of sigma would be 0 because insulator doesn't have conductivity, right? So it will go like this if it is insulator. I'll show you it in the top one. Okay. Next, reference. You may have learned this formula, right? These are the formulas called Fresnel formula from electronic theory. Okay, whether you learn it here in this on the bridge program here at Phi, I believe the students learn this formula twice when they are in the first year. They already deal with this formula and they start to go deeper. Yeah, I see it when they study electromagnetic wave. So this is from now formula. So this is the description. So if we have medium 1, medium 2, right? We strike the light, it gets reflected, it gets refracted. So there is theta I incident, and so this is theta R reflected light, and this is theta T. Okay. T means transmitted. So all these indexes I, T, understand. Okay. 1 means maybe 1, 2 means maybe. Okay. Okay. But we are more interested only in seeing the situation where the light is coming with normal incidence, meaning theta I and theta T both are equal to 0. And in this case, we simplify our situation by considering that the medium 1 is just air or vacuum. Okay. So N1 is what? And N2 is the material electricity to explore. Okay. So we call it n omega, n of omega, or and the n of omega is square root of epsilon r, complex number. This is what we learned in the previous pages. Okay, and all the complications that these two formulas are showing is simply by us simply considering just the natural light. So when we consider natural light, we both actually these are S stands for S polarization, meaning S means the electric field vector is perpendicular to the plane of incident, whereas P means that the electric field is on the parallel to the plane of incident. Okay. When you study electromagnetic theory, these details need to be considered very carefully. Okay, but for our purpose over here, we simply take the average, so we don't need to care about. Actually, this is RS, this is RP. Sorry, this is actually RP. That's a typo. So average of RS and RP give us simply take this to be 1, right? 1 cos of 0. So this is a formula. Very simple. Okay. So once we know the formula of epsilon 1 as a function of frequency, epsilon 2 as a function of frequency, then basically we can write small code to do the computation to compute the reflectance. Then we can get the curve of reflectance. Okay. So here's the curve. Look. This is the epsilon 2. I was already showing before, right? This is the epsilon 1. I didn't, I'm not explaining here the LF. But now I have the reflectance. So the reflectance that I obtained from the formula I showed before give us this kind of behavior. Look, what is interesting? Look at the value. When omega is so small, the value of the reflectance is near 1. Okay, as it goes up, approaching this border. What is this border? This border is the omega p. As it approaches the omega p, it decreases a little bit and suddenly jump abruptly to 0 and then increase a little bit. So this is the behavior. Okay, it's the behavior. So what's the physical consequence of having reflectance value being close to 1? That means the reflectance is 100% or almost 100%. And that's the typical characteristic of all metals. All metals. Okay? Common metals. By common metals, I mean things that we usually we call them metals. Okay? If we don't really agree to call something as a metal, well, there may be some problem there, and we don't know how the reflectance don't behave. But normally, if you name any material that most people really call it metal, like steel, right? Aluminum, copper, they're all metal, right? They behave like this. All of them. Okay? And this is an important point also, that I put some marking in a certain region over here that I denote as the region of visible light. So this is the region of visible light. Meaning all possible lights fall into this region, which corresponds to reflectance value equals to almost 1. Even if not quite 1, but still very, very close to 1. Okay? Meaning most of metals are really good. Okay? Just correction. Okay. Ah. Unknowingly, I may have signed out from the Zoom, though, but the operator is not saying over here, so anyway. Okay, let's get to this page. Oh, by the way, since the alpha time is 320 here, the I think 321 or something, 320 or 3. So why don't we just stop right at after time? Then we'll have a 30 minutes break and we'll come to this. Okay? There's some install over there, you know. So we'll come back after the break of about half hour. Okay. Now the curve that I showed you in the previous page here, this is just the curve. A model that is so simplistic, you know, where you neglect a lot of things, but you still keep some important ingredients. Okay, so this is kind of one model. But nevertheless, it gives us good results. Right? So that allows you with basic papers often when the authors use one model of the title of the point model or something. But of course, by saying oh, it doesn't mean that the paper goes to just low low level now. That doesn't mean so. Point model can be a way of explaining something that if we are not smart enough to keep what is the most important ingredient to kept in the model, and we are just tempted to just consider everything, then our model may never become simple enough. Then there is no easy explanation that we can propose, right? But if we are smart enough, be able to select which which mechanism that may give the main behavior, the main operating system, then we propose model that's a simple that only is this ingredient and negative to us, we come up with a toy model. The toy model that for example here, the model is spectacular. And this is one thing. So this is the theoretical result or the toy model result. Battery problem. Yeah.
May I ask?
Yes.
Please make a index.
What is omega p? You're asking about the relation. Okay. In the previous explanation, P, I already explained the P stands for plasma. P stands for plasma. Why plasma? Okay, if I have to go through the explanation, plasma. Are you familiar with the term plasma? What is it? Huh? I don't have to get. So if we have a gas of about equal amount of positive and negatively charged particles, then we have plasma. So we have plasma in metal. We consider electron gas in metal as plasma. State charges also. Although the positive charges are not moving, they are not moving, but they are there to compensate the total charge to be conserved. Okay, that's why we still consider system of electrons in metal behave like plasma. That's why it's a plasma absolutely negative. Okay, and I probably forgot to tell you the very similar, basically the same phenomenon, very perhaps in a different scale. Plasma that is in ionosphere. So we know that ionosphere is called ionosphere because it's the best ion, right? So it actually the best plasma. And it exactly behaves like plasma of electrons in there. How? How does it behave the same as what we see in matter? Because in ionospheres, so the difference is actually in metals we have negatively charged particles that are moving and positively charged particles pretty much at rest, pretty much they are static. Okay? Whereas in the ionosphere we have both moving, but that difference doesn't make significant effect to the conclusion. So it turns out that we can simply use the theory that we have discussed just before to apply to ionosphere. Therefore, ionosphere also has this behavior. I mean, the epsilon 1 looking like that, okay? Epsilon 2 looking like that. And it also has some negative region, right? Some region where the epsilon 1 value is negative. Meaning in that region, the ionosphere reflects the electromagnetic wave. Just like metal reflects light, visible light. But of course, there's a difference. What is the difference? As you have seen before, that it has some formula. Depends on the what? N. What is N? Yeah, well, I also use N for representing index diffraction, but when I say N in the formula of omega P, what is that N? Electron density. So I've used N for two different quantities. There was N, then electron density, number how many electrons we have over volume. Okay, that's electron density. That enters the formula of omega. I don't know if you took note or not, but I will give you this material. So N in the formula of omega P represents electron density. a particle is. And there's also M. It is too far to go back. That's why I'm like to go back. Okay. So anyway, there is M. There's also M. Right? M is what M is that? What mass is that? In the case of electrons in metal, the mass of the electron, right? So when we bring this same idea to explain what happens in ionosphere, the basic is the same, but of course, M should be presenting now not the concentration of electron anymore, but the concentration of the gas, right? The concentration of the ions in the ionosphere. And the M also is not M of electrons, M of the average mass of molecules and molecules in the atoms. Therefore, overall, the value of omega p for the ionosphere is bigger or smaller compared to the one of electrons in higher or okay. Let me give you a hint. The formula is square root. Inside there is a ratio on the top. You have n. In the bottom you have n. Now your n for the metal is much smaller compared to n for ions. That already indicates that you tend to have omega p for the ionosphere bigger or higher or lower, much lower. So the physics is the same, but the omega value is much lower. If the omega value for the metal correspond to I said before it is of order of UeV. UeV means on the order of UV light, UV light. Higher frequency compared to visible light. Okay, visible light only up to maximum, I guess, 1 eV, 1 point something eV. Okay, if it is already 2 eV or 3 eV, that's already UV. Okay, so therefore, all visible lights, since they are all smaller in frequency compared to UV, compared to the omega p of metals. In most cases, then that's why metals are always. And ionosphere, the omega p is of the order of microwave. Microwave is about microwave in terms of the lambda, it is of the order of centimeters of or operator. It is my thing. You can convert into the frequency here, the energy here, okay? And that means since omega p of ionosphere is that low, then ionosphere can only reflect gas, the electromagnetic waves that have frequency below the frequency of code. Okay. Now, the idea of what frequency values we use for computation will be ours. Radio wave. Radio wave is basically of the same order as of the ions. So there may be some radio wave that can exceed the omega of ionosphere, so that it can go to the outer space. because that's doesn't get it like okay. That is the difference. But there is no sound. See become. Right? Consequence together. Okay. Actually, most of use the communication on the fact that help on the speed, so that we can easily transfer okay, from one point on the earth to another place on the other side of the earth, right? Because otherwise it will be possible. See, imagine you have a sphere of earth. If you have if you transmit a signal from somewhere over here, the signal will spread somewhere, go there and there. If there's nothing that reflects these signals, right, it will never reach the other side of Earth. It is actually the role of that service for you, right? Of course, that is what is the nature does. But of course, to improve the quality, because of the videos. But without the help of ionospheres, it is impossible. Okay. Okay, now look at this curve. This one in the inset are the curves for experimental data. Silver, aluminum, and gold. Okay, these are experimental data, and this is the model. This is actually from the Drude model. The same formula that in experience. The only difference is just the way I'm plotting it. Okay, just the way I'm plotting it. The difference is that before I plot the curve against frequency omega. Now I'm plotting it against lambda, and I do it in the log scale. Why I do this? Because experimentalists like to do it that way. So in order for us to be able to make a comparison, often we have to adapt ourselves the way they like to show their curve, so that rather than doing it the way we derive the formula, somehow we have to adjust a little bit the way we show the curve. So this is nothing but another way of showing the same curve, only that the horizontal axis is converted from omega to lambda. Okay, that shouldn't be very difficult for you to digest. So just by playing the parameters that we have in the model, we can select the parameters such that we get well, actually we are not just playing with parameters, we are using the parameters, the empirical parameters of the research. We plug in to the formulas, then this is what we got. See, amazingly, they look similar, right? They look similar, even though this comes from very simple model. This is reality. This reality, they look similar. Okay. And where is the region of visible light? Region of visible light is this region, which is around here. Well, we actually expect that the visible light is exactly over here, but it is difficult for us to make a clear cut because the scale is low. If the scale is linear, it's much easier for us to put the border of the where the lower limit and higher limit. Anyway, I'm just showing you that no matter how simple model is, but it can help a lot and plays an important role in explaining in being able to explain the phenomenon. Okay, this is just some additional material. Although I've shown you how to obtain both real and imaginary parts of epsilon, but theoretically, if we already obtained one, then we can obtain the other one, because those two quantities, real and imaginary parts of physical quantities are related through what we call Fermat's-Cornell relationship. I suppose mathematically this is to learn when you learn math physics also. Right? I suppose this is part of Fermat's-Cornell relationship is part of complex variable subject. So every physical quantity that has separate dependence and has some behavior where dependence is in such a way that as omega goes to infinity, it has to go to zero quicker than certain 1/omega without something that kind of behavior. Okay, so once function fulfills that criteria, okay, then that fall into quantities that can be connected to transform. Okay, and in this case, epsilon and sigma both can always be related the real and imaginary part using this reference. So this is important for analysts to make our calculation. So we don't need to calculate both. Once we calculate just one, and the other one is simply calculated using this ratio with mass factor. Okay, now we come to thermal micro integrators. Okay. This is still the Lorentz part. The one involved the truth. Okay. What is the difference between insulators and metals? What is the main difference? From the point of view of simple physics, if you already talk about magnet, that means you already knew the mechanics there. So we don't have magnet unless we have quantum mechanics. Let's suppose that we don't know yet quantum mechanics. Then what makes the difference between metals and insulators? Yeah, that is the characteristic. Okay, and that's the characteristic that we observe. I mean, what is happening inside? Yeah, exactly. So when we talk about metal, talk about PLA, right? Well, ideally they are free. Even if they are not so free, they mostly behave as free. Okay? So that is for. Whereas for insulators, you can think of the electrons all being bound to the nuclei, right? So when we want to model it, then this is what we see. Okay, so imagine that we have the atoms. We have, of course, we have many electrons, but I just show one electron, for instance. So every electron that is bound to the nucleus can be viewed in a very simple way, as if it's tied to the nucleus through a spring like that. Of course, the interaction between electron and nucleus is Coulombic. Coulomb. At some point, Coulomb interaction can be approximated to parabolic, parabolic interaction, parabolic potential, which corresponds to assuming that what ties the electron and the nucleus is continuous. Okay. So if we shine that one wave in the insulated, again we have exactly the same way of thinking, right? We have the E like this, and then we have the R like. Okay. Then we have the equation of motion, Newton's equation of motion, and the additional term that we didn't have before is this one. So before for metals, remember, for metals, we don't have this term. Okay? And another thing that we have to keep in mind when we think about metals, we say that the electrons are free. So they are moving. Okay, they are mobile. They are moving around. Now they are actually bound like this. Of course, there is still motion. The motion are just observation. But yet this all the other terms before this one, they are still the same. So we only add this term, which is what force is this? What do you call this kind of force? What law? Hooke law, yeah. Minus kx. Instead of x, I put r. But instead of k, I put m omega squared. Right? So this leads to this. Okay. Next, you obtain r, that, and then p. Okay, if you pay attention to the structure that we obtain here, it is simply actually a correction. It is only in a way that before we didn't have this omega naught squared. Now we put this minus in every appearance of omega naught squared, we subtract. In every appearance of omega squared, we subtract with omega naught. So this is okay. Let me speed up. Okay, going through the same steps, but the formula that comes up, of course, different. Okay, and correspondingly, we also obtain sigma 1 and sigma 2. This is the reason. Okay, look at the sigma curve. If I'm asking you, what is the value of, so the blue one is the conductivity curve. Okay, so what is the DC value of the conductivity of this insulator from the curve? Can you tell? What is the DC value of? DC value means the conductivity value corresponding to the static field, which means 0 omega. Okay, and omega equal to 0. According to this curve, 0. Okay, this curve is obtained from the formula. Okay, but if we interpret the 0 value that is consistent of the characteristic of insulator. Insulator has zero conductivity. And in fact, it is not just zero at here. It stays zero as we go up the frequency. Only up to approaching omega naught, it raises up. But before that, it keeps zero. What does that mean? That means even if we apply amplitude from the automatic wave with some frequency dependence, okay? The zero conductivity means that the electrons don't respond. Okay? If the electrons don't respond, it means they will let the light. It is not true. Therefore, the main characteristic of insulator actually is a transparent tube. At least according to this theory. Okay, of course, the theory is not the most correct one. This is a classical theory which doesn't incorporate quantum thought. Okay, but nevertheless, the characteristic around here is already captured by this simple theory. Okay, so I want you to appreciate this theory because you are also physics. If you are a physicist, okay? Don't behave that you only like dealing with physics that sound fancy, sound difficult. It's not difficult at all. But actually, we don't understand the simple. So that's not okay. In order to claim that you want to like to deal with physics, that you feel that this is the true physics, the most physics of physics. Okay, this is a difficult one. It is good if you are really interested in physics. Yes, you have a passion in research, but don't have the behavior, that kind of behavior if you skip to try to understand the simple. Okay. Start to like the difficult one, not because they are difficult, because you have understood the more easy ones. Okay. As you go out, try to understand more completely about the more complete explanation of every phenomenon. The way you learn is by understanding this that from the easily more really for until you need, if you really need to deal with very difficult, then you do it not because you like the difficulties, but you really believe that by understanding the phenomena completely, there is some benefit, there is some advantage that you will get. Okay, so that has to be the. Okay, so I just have to stop. Okay, let me finish explaining this. So finally, the reflectance curve looks like this. Okay, look that there is also part of the reflectance curve of this insulator, right? There's part that has the value close to one, We understood before if reflectance value is close to one, that means for this frequency, the material is reflecting. Okay. But the question is, where is visible light region? Typically, visible light region is over here, not over here. Okay. So when we want to talk about how insulators respond to visible light, we need to look at this region. And this region, the reflectance value is very small, right? Indicating that only a little amount of light energy that is emitted. It's not zero, but little. It's okay. It reflects, but just reflect a little bit. Most of the energy actually goes to. Okay, so this will be taken by this. Okay, whether or not that makes the light that already goes inside the material will make the material transparent or not. It will depend on whether there is some other mechanism, whether we have absorption, secondary. Okay? So at the moment, we are not talking about those. So we are assuming that there is no secondary, there is no absorption. Happens if not was affected or goes through. Okay? So then this is the okay. Okay, so let's have a break for 30 minutes. So we'll start again now at 3:30. What's the time? Now 3:30 exactly. So let's resume the class at 4 o'clock. Okay.
I'm bold that goodness. Oh, oh, that's it. So that's all much. About. It's not I mean, they would. I must say, you consider the idea and he. It is so. Yeah, so when so this and then what please ninguém usa gosto disso. Olha, bisa gosto, terus kita mesti berapa kali bahas orang tuh yang mana? Pantas. Simpan sorry tadi. Kayak gini.